A firework is a chain reaction of chemical reactions. A firework has a fuse, which most people know about. It can come in various different points of the firework, but quite often you see it kind of like that. A fuse can be as simple as paper or as complicated as an electric charge like professionals use, connected to a computer to set off the fireworks at just the right time. There's a broad spectrum of options in between. It also has black powder charge, which is a propellant, also known as a lifting charge. It will shoot the whole thing up into the air like a rocket. These are typically made of gunpowder, as the name black powder implies, and a few chemicals added to it. We'll get to that in a second. For fireworks with tracing tails, there will often be balls of other chemicals laced into the charge. There's also a time fuse right here, which is exactly what it sounds like. It gives a few second delay so the whole thing can reach its desired height before it goes off. The time fuse leads to the bursting charge, which is sometimes called the head. It ignites and explodes, shooting out the effects, or stars, these little balls here. These are round chemical pellets that can range in size from the size of a pea to the size of a golf ball. The chemicals used determine the brightness and color. The effect is the final destructive output. Otherwise it'd be a lame rocket. An aerial shell has a cardboard casing known as a mortar tube. The bottom has a little bit of black powder, which serves as a propellant, and sometimes the fuse goes out the side. Here in some of the used fireworks you can see the empty mortar tubes. Some of them still have some stuff in there, some packaging material. So how do these chemicals work? Every time you have something that is pyrotechnic, you have to have a chemical that supplies the oxygen, an oxidizer. The reaction needs oxygen, and the oxidizer supplies a large amount of it rather than just taking it from the air. This is why fireworks can still go off even if you smother them. They bring in their own oxygen, so it won't extinguish itself like a traditional fire. Potassium nitrate is the oxidizer we usually see in fireworks. It's used in gunpowder. Potassium perchlorate is used in a lot of color combinations. Strontium nitrate is also oxygen-rich, and it produces a nice red color. You also need fuel. Oxidizers don't do a lot without fuel. These fuels can be things like sulfur, which smells really good when you mix it with hydrogen. Charcoal, which is really common, which was originally used in fireworks when they were first created. Aluminum powder and magnesium powder are also used. You vary your fuel to get a specific heat output and burning rate. Colors are produced by specific elements heated to high temperatures, which will release a specific wavelength of light. Ions are important because unpaired electrons absorb light. In ionic compounds, it's the cation, or the positive part of the ion, that determines the color produced. Sodium, like in sodium chloride, table salt, produces a yellow flame. Strontium makes red. Calcium makes a cool orange. Barium makes green. Potassium makes a light purple. Titanium makes a silver white. For blue, they used to use arsenic, which worked really well, but since it's poisonous, they didn't want to go scattering that around. Lead also makes a nice blue color. Again, we don't want to be scattering that all through the air. So now we use copper to make blue. But copper will make green if you get it too hot. So to make blue, the copper can't be too hot, but it has to be hot enough that it's actually glowing. So it has to be Goldilocks range there. Not too hot, not too cold, just right. It's in my mouth. In fireworks, you start with the oxidizer and the fuel, and then you add whatever else you need to change the color. In an atom, you have electrons. Wow! Electrons are at specific energy levels. They like to be in a state that requires the least amount of energy. I like Netflix too. This is called the ground state. When a bunch of energy is added to the electron can jump up to the next energy level. Whoop. They don't sit halfway through though. They're not going to do that. No, 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 no. They're going to be on this level, or even this level, or this level. They're always going to be on one of the levels. It's like rungs of a ladder. You can't stop halfway between rungs. You have to be on one rung or another rung. This abrupt change in the atom is known as the quantum jump. The electron goes to a different energy level. Sometimes it goes one higher, Sometimes it goes 2 higher. Sometimes it goes 3 higher. Either way, it always goes to a specific energy level above what it was before. When the electron has jumped to a higher energy level, this is called the excited state. So exciting. But as with a lot of exciting things in life, this is unstable. So the electron's going to fall back down to the ground state. But remember, we added energy. We put energy into this to make it jump up. Energy conservation, energy in, energy out. So we have to get rid of the energy. The energy is going to leave in a little wave packet, known as a photon. When people talk about light being both a wave and a particle, this is what they mean. It acts kind of like a particle, but it's also a wave. So it's like a little packet of waves. Sometimes we show the same thing in a line format instead of rings. So it's a little bit simpler. Just have your electron at the ground state, add energy to it. It does a quantum jump to the excited state. That's unstable. It falls back down to the ground state. And in the process, it emits a photon. It's basically like we've graphed this, except for there's not much of an x-axis. It just kind of shows the different levels you will get. The difference in energy between the two shells corresponds to the wavelength of the light emitted. There are lots of electrons, and each element has a different amount of electrons, and often different amounts of electron shells. So the color emitted is the mix of wavelengths of the atom. You may be familiar with the color spectrum. Different colors of light have different wavelengths. I won't go to math right now, but the size of the quantum jump is related to the energy input, and therefore energy output. The E here is for energy. The more energy, the higher the frequency. This is the symbol for frequency. So as this gets higher because this is a constant. Wavelength and frequency are inversely proportional. So as one goes up, the other goes down. So the higher the frequency, the smaller the wavelength. So low energy would be towards the red end of the spectrum, and high energy would be towards the blue or purple end of the spectrum. Charcoal in fireworks is mostly carbon, which when it's burned combines with the oxygen in the air to produce carbon dioxide. The reaction then releases energy in the form of light and heat. Add more oxygen and the process speeds up. Fireworks are basically supercharged combustion reactions. They add tons of oxygen, but not from the air, from the oxidizers, commonly potassium nitrate. Food is full of carbon too, and the same process is happening in our bodies as in fireworks. It just happens much, much slower. We take the oxygen from the air that we breathe, the oxygen combines with the carbon in our food, it produces light and heat. This heat is our body heat. It keeps us warm. It's just enough, nice and slow. The light is infrared light. If you're human, you probably can't see the light that humans produce, but those of you out there who can see infrared will be able to see the light that humans produce. Both in fireworks and in breathing, we produce carbon dioxide. That's why we breathe it out. Calories in food are the measurement of how much energy is released when the food literally burns. I like to call them delicious points. When I was a kid, the dad of one of my friends was missing his index finger on his right hand, part of his hand right here, and the top half of his thumb. Obviously the top half, he couldn't lose the bottom half and keep the top half. Anyway, this happened because when he was a teenager, he decided to make some homemade fireworks. He lit one and it didn't go off, so he figured it was a dud. He went and grabbed it, and that tiny disturbance of just grabbing it was enough to set off the reaction and cause the firework to explode. Thankfully, it was a small firework and he only lost 1.5 fingers, which would still be very traumatic and incredibly painful. He's lucky he didn't lose his life. Moral of the story is that fireworks are amazing, but you still need to be super, super careful and take precautions. Don't get complacent just because you use them so frequently. Whoa! Final. Ooh. Woo! Hello! The stick went up my skirt. That was awesome. Ow! Got it in my...